Hello AP Chemistry and welcome to 14.3 Concentration and Rate Laws. So first of all, when we say write a rate law or provide a rate law, this is a rate law, okay? It's an expression, right, that always consists of rate, and most of the time we're actually going to literally write the word rate equals K times this format, right? So let's say we're talking about this reaction up here, right, where these are our coefficients, right? And these are my species, okay? So we'll see in here, right, that this is the concentration. These are both concentration, right, of species A and B, right? So these are always going to be concentrations of my reactants, right? And square brackets again means, right, molarity, okay? Rate is going to be my rate, obviously, which is often going to be measured in, right, molarity per second, okay? And to be mindful, when we say molarity per second, molarity is composed of moles per liter, right? So this could also say moles over liters times second, right? Which means it could also say, right, for example, moles times liters to the -1 times seconds to the -1, yes? Right? There are lots of variations on this. Just make sure you pay attention, right? And you know enough math to be able to discern what it's actually saying. Okay, over here, right, then we have our K, right, always lowercase, right, always lowercase, because in the next chapter we're going to start talking about capital K, which goes back to what we talked about in thermochemistry, right? But lowercase k is always going to be the rate constant, right? Now, the rate constant is temperature dependent, right? Which means that if we say that we're running this reaction at 250 degrees Celsius, that means this K applies at 250 degrees Celsius, okay? But it is a rate constant, and it does give information about how quickly a reaction occurs, right? Like your textbook says, if it's greater than 10 to the ninth, really, really fast reaction, right? If it starts to get down into single digits, means super duper slow reaction, okay? So rate constant just gives us a little bit of information about how we can classify the rate, right? Is the reaction fast or slow? Up here, we have these two pieces of information, M and N. And note that none of these say M or N, yes? Please, please, please keep that in mind. These are not coefficients, okay? Not coefficients. All right? These are experimentally determined rate orders, meaning that the only way we can come up with M and N is via experimental data, right? Or we could be given the values of M and N, but they don't come from a balanced equation, right? Really, really important to keep that in mind. In the next chapter, we will talk about things that work that way, right? But when we're talking about a rate law, okay, these exponents are rate orders, which come from experimental data every time. Okay, so again, when you're asked to provide a rate law for a reaction, this is what you're writing. Okay, so this practice exercise says, what is the reaction order of the reactant H2, right? And these are our equations over here. So if we look here, what is the exponent of H2? Right, 1. So the answer is 1. That's it, because that's the order of H2. Now, if we were asking for the overall order, right, it would be 1 plus 1. So the overall reaction order would be 2. Okay? So what are the units of the rate constant for equation 1411? So that's the one thing we skipped over in the last one, right? But we know that rate is going to be molarity per second. Okay? We know that this is units of molarity. This is units of molarity, right? So we have molarity times molarity times K has to equal that, right? Which means that this is molar squared. So if we divide both sides by molar squared, which means, so my unit then is what? Right, 1 over M times S is the unit for K, right? And that's how you're always going to deduce the units of K. K is always going to be based on whatever else is there, right? So if one of these were a second order, right, then this would change that, which would change this, which would change my units, okay? Anyway, so that's always how we're going to deduce the units of K. It's always going to be what is everybody else's unit, and whatever's left over is the unit for K. And again, like we talked about at the beginning, right, this can be expressed in lots of different ways, right? This can be liters over moles times second, for example, right? lots of different ways you can write this. Just make sure you're paying attention to what it actually says. Okay, next up, how exactly do we find m and n from data, right? So in terms of the data that we're going to be looking at, right, because that's important to keep in mind, we're going to be looking at trials, right? So we're going to have a certain number of trials, and we're going to have some initial concentration information. So this is also called, right, finding rates from initial concentrations, right? And this is our observed initial rate. So if we look again, right, we have trials with initial concentrations and rate data, okay? Now, if I want to find the effect of NH4 plus, right, if I want to find what effect this has on the solution, what I'm going to do is I'm going to look for trials where NO2 stays the same, right? If this is a reaction between these two things, right, if I keep my NO2 the same but vary my NH4, then what that means is that a change in the rate would be due to the change in NH4 concentration, okay? So if we look here, right, if we look at these two trials, for example, right, the rate of it, the concentration of NO2 stays the same, this doubles, right? So that doubles. We look over here, what happens to the rate? It doubles, okay? And so in terms of how we figure this out, right, it's the change in concentration raised to what power gives us the change in the rate. And in this case, the x is, I should have used m, is 1, which means that this reaction is first order with respect to ammonium. Yes? Meaning that whatever effect we do to the rate, to the concentration, has the same effect on the rate. By extension, right, if we think about quadrupling the concentration, we also quadruple the rate. Yes, do you see that? Okay. If we wanted to find the effect of NO2 on the rate, we would do the same thing right here. We would look at these. This stays constant. This doubles. As that doubles, this doubles. So again, 2 to the what gives us 2, right? This would also be first order with respect to nitrite. Okay, another practice. So it says the following data were measured for the reaction of nitric acid with hydrogen. And so we have some trials, we have some concentrations, and we have some rates. So determine the rate law, right? So again, rate law means rate equals K times my concentrations raised to their respective orders. So that means I have to figure out what my orders are. So if we look at my NO concentration, it stays constant here. This doubles, right? My H2 doubles. My rate also doubles, which means that it is first order with respect to H2. If we look at NO, so we could pick these two trials, for example, okay? And we look here, because H2 is constant. Here, this doubles. My NO doubles. What happens to my rate? Right, if you need to, you can type it in to divide it, right? But as my, that changes, this goes up by a factor of 4, which means that what is my exponent now? Right, 2. So this reaction is second order with respect to NO, meaning that whatever effect, whatever change I impart on the concentration, it's going to be double that effect on the rate, basically, okay? And H2 is first order. So this is my rate law for the reaction, and this would be the answer to A, okay? And in terms of showing your work, right, that's what you would show, right, is that, for example, for this one, it's like 2 to the m equals 2, therefore m equals that, right, and this one equals that. Okay, for B, calculate the rate constant. So how are we going to do that? Right, it's constant. Doesn't matter what my concentrations are, so pick a trial. If we want to use one, we would plug in my rate, we would plug in my concentrations, and we would solve for K, bearing in mind that for my units, right, this is going to be molar per second, molar squared, molar, and then I would work backwards to figure out my unit for K. All right? When it says to calculate the rate when this equals that, right, then we would plug in my concentrations, right, and we would plug in the K that I just solved for, and we would solve for the rate. Yes? Yes. All right. The only tricky part about this, right, is paying attention to what kind of data do I have, and then how do I get my m and my n. Then the rest of it is just using the equation. All right. Thank you for listening. Be good, and I will see you soon. Bye.